Okay, so where we left off, we were looking at these connections between linear and angular kinematics. So I want to show just one brief thing real quick. So we say that V is equal to R omega. If I go ahead and I substitute that into this equation, I would have R omega final equals R omega initial plus, for acceleration, that's R alpha t. Now all of those r's are the same, and so what you'll notice is what I end up with is this equation right here. So these are kind of the barrier that converts from linear to angular. And so what I often say is what you would do for linear motion in a given situation is exactly what you would do 90+% of the time for angular behaviors. So let's try a few problems and see if this makes more sense. So here we have a crankshaft on an automobile that is rotating at 2,500 rotations per minute, and we want to convert that into radians per second. So we have 2,500 rotations in 1 minute. Now, one rotation is 2 pi radians, and 1 minute is 60 seconds. So we're going to go ahead and we're going to come in here. We're going to go through our units and do a little unit cleanup here. So when we start multiplying things across, we're going to get 5,000 pi. And we're going to divide that by 60, and that's going to lead us to 261.8, or 262 radians per second. So if we have a spool of thread that's unwound so that the thread 8 meters long is hanging off the spool, and the spool is 2 centimeters wide, we want to know what angular displacement occurred. So we would be using that S is equal to R theta. We know we have 8 meters. That is going to equal our radius would be 1 centimeter, or 0.01 meter. And then our theta, so we would have 8 divided by 0.01. So that is going to give me a theta of 800 radians. If I divide that by 2 pi, I get that that is going to be 127.3 rotations. So try number 3 on your own. So let's look at this problem. We have a rider on a merry-go-round moving with a constant linear or tangential speed that is 2.69 meters per second. We want to know what is the angular speed. So this is our linear speed. Now we know that the linear speed is equal to r times the angular speed. We have that the radius is 3 meters. So 2.69 is going to equal 3 times omega. We divide both sides by 3. And so that's how we're going to get that omega is about 0.9 radians per second. Now if we want to know the time it takes to reach the opposite side of the ride, what we could do is we could look at theta. So theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. Well, we have something that's going to let us cancel some of this out, and that's the constant linear. That means that our alpha is 0. So we're starting at a spot, we're going to call that 0. We know our omega is 0.9. We're looking for time. And then we want to know where it is when it goes halfway around, so to the opposite side. That is pi radians around. So we're going to take that pi, we're going to divide it by 0.9, and that's going to give us a time of about 3.5 seconds. Now if we want to know how many revolutions are completed in a time of 2 minutes, 2 minutes, that is 120 seconds. We can use the equation we just had there. So we're going to simplify it. We're just going to do the omega naught t. So theta is going to equal omega t. So that is going to be 0.9 times 120 seconds. Now that is going to give us our theta in terms of radians. So keep that in mind. So I've got 0.9 times 120 seconds. That's 108 radians. So if I think about my conversion, I have 108 radians. 1 revolution is 2 pi radians. So I'm going to divide 108 by 2 pi. And that is going to give me 17.19 or 17.2 revolutions. So now let's suppose the ride is made to stop. And it stops while completing 0.75 revolutions. We want to know what is the angular acceleration that the rider is going to experience. The very first thing that we are going to need to do is to convert this revolutions into radians. So we have 0.75 revolutions. Each revolution is 2 pi radians. So this is going to be 0.75 times 2 pi. So that's going to be 4.71 radians. So what we have an initial angular velocity, we have a final angular velocity, and we have a change in the angular displacement. So we're going to be using this equation to allow us to solve for the acceleration. So we have 0 is equal to 0.9 squared plus 2 alpha, 4.71, it's our change in theta. So I get negative 0.81 is going to equal 4.71 times 2. So we're looking at 9.42 alpha. So I'm going to divide that 0.81 by the 9.42, and I'm going to get the angular acceleration equals negative 0.0859, so 86, and that's going to be in radians per second. Now, this conversion piece is a Burmese tiger trap. If you are not paying attention, it is very easy just to plug that 0.75 in and not think twice about it. Be careful there. So if we want to know how much time it takes to come to a stop, we could use our angular velocity equation. We now have our alpha, so we've got that 0 equals 0.9 plus the alpha, so negative 0.086 times time. So 0.9 divided by my acceleration. My time is going to give me 10.47 seconds, which would round to 10.5 seconds. And if we want to know the tangential acceleration, what we are going to do is we are going to take the radius times the tangential acceleration. That's going to be the radius times alpha. So we're going to go back up here a little bit, and we're going to grab our radius. So our radius was 3 meters. So we're going to take 3 meters times our acceleration we just had. So if I take 3 times that 0.86, that is going to give me negative 0.2578, so 0.256, and that's going to be in meters per second squared. So I'm going to challenge you to look at G and see if you can figure out which one is which. See if you can puzzle out which one is which. Is the angular velocity for child 1 going to be less than, equal to, or greater than the angular velocity for child 2? So puzzle through that, and we'll come back.